Hi, I'm super excited about this one. Thank you very much to Omicron Lab for sending in this baby in this very sexy case, which I believe is optional extra, but let's check it out. Let's check out the Bode 100. We'll have a look at all the stuff, but, oh, hang on. Oh, I just smell versatility. Look at this. We've got the Omicron Bode 100. Basically, it's a vector network analyzer, but different to the RF vector network analyzer that we looked at in that previous Siglant video. This is a much more versatile bit of kit for your average, electronics design engineer. Let's take a look at it. So in this box, we get two passive probes, which I think are optional extra as well. I think everything's basically optional extra. I think you just buy the base Bode 100 unit, but I'm very excited about this. We've got a wideband injection transformer. We'll go into that. I've been wanting one of those for ages. I've been thinking about building my own. That'll have to be a separate video. Oh, look, a passive component measurement test jig. And another passive component measurement chest jig should take a look at. We've got a power supply, then we've just got various probes and things, a test board, whatnot, various coaxes and stuff like that. Cool. Let's check out what this thing can do. So what is this thing and why am I so excited about it? Well, it's basically a vector network analyzer, as I said, or an impedance analyzer, whatever you want to call it, but it does have vector network analyzer capability. But instead of, as we saw in a previous video, being for RF type stuff, this is basically from DC to 50 megahertz bandwidth. So it's much more useful for more practical electronic stuff. Things like, measuring the stability of control circuits, i.e. power supplies, which I'm going to have to do a totally separate video on because that's like a 30-minute whiteboard thing in its own right, via one of these voltage injection transformers. And I don't think I'll be able to demonstrate that in this video. Maybe. We'll have a look. So that allows you to measure the performance and stability and calculate what sort of output capacitors and things like that you need for not only your own DC to DC converters, but for off-the-shelf linear regulators and stuff like that. You can do complex impedances of various components. So I've done that before in an old video, which I'll link in down below, where I used a red pataya to measure the impedance over frequency up to, I think, 40 or 50 megahertz like this one does, but I use that red pataya to measure the parameters of a bypass capacitor that you typically use on a board. And that video, well, we did get a plot out of it, but it was a bit meh, a bit how you doing. This, though, the Bode 100 is a professional bit of kit for actually doing those sort of impedance measurements on individual components, capacitors, inductors, and all sorts of things. We could do things like measure the complex impedance of power planes and the effectiveness of bypass capacitors. I want to do a whole video on that. Given the frequency range, you can measure resonance stuff for things like near-field communication stuff. You can measure the performance of crystals, piezo transducers, and of course you could do like filter, swept filter performance curves, amplifiers. You could do EMC stuff, a whole range of stuff. So having a DC to 50 megahertz vector network analyzer or impedance analyzer, it's a much more useful bit of kit for your average, electronics engineer just designing, like piece of non-RF type stuff. It just allows you to do a whole bunch of things, and I can't wait to see, I can just think of like half a dozen videos off the top of my head that I could use this bit of kit for, that really I didn't have the capability to do it before this. So thank you very much, Omicron, for sending this baby in. I've been actually trying to get my hands on like a 100 megahertz or a DC to 100 megahertz vector network analyzer, like secondhand old HP or Agilent one or something like that on eBay. But this is like a modern USB type one, and it's got all the software bells and whistles that we could possibly need. So this will be a review video, and I won't be tearing it down in this video. I'll link in a separate teardown video at the end if you want to see how this baby works. And basically we've got a signal generator output 0 to 50 megahertz. I'll put up the specs here so that you can see the entire performance specs for this thing. And then we've basically got 2 inputs in here. Now you don't have to use them all the time. You can get, depending on the measurement configuration, the thing that you're actually trying to measure, you might use one or both of these inputs here. And as I said, everything's optional with these. A wideband injection transformer, like test jigs for passive components. You whack your little surface mount component in there and it probes that. Oh, that's just, isn't that just sex on a stick? Look at that. Unbelievable. And then we've got our main unit, which is actually very nicely designed and constructed. I really like it. We've just got a 10-watt plug pack input here, an earth-in terminal. You might need that depending on your system configuration, and a simple USB type input. So this is a very nice bit of professional kit, and it'd want to be for the price, because this is about 5,000 US bucks, and you might choke at that, but hey, try and get a professional 50 megahertz Vector Network Analyser for less that can do all the stuff this one can. I think you'll be hard pressed. They included some probes which feel very nice. Oh, that's ridiculously sharp. Unbelievable. That's probably the nicest probe I've ever felt. The rubber on that. Beautiful. Made in Germany. Oh, this is just absolutely gorgeous. You just got to feel this thing to know how good a quality this is. Manufactured by PMK, is it? I don't know. Designed for Omicron, and it's just a 10-to-1 scope probe, 50 meg bandwidth, because that's the bandwidth of this thing, and 12.5 puff. It's not particularly low capacitance, which might be important. If you're doing that, you'd have active probes or some other solution. But that is very nice. But they're optional. And this bit of kit is a wideband injection transformer, the WWIT100. They actually make a couple of these. One is designed for even lower frequencies than this one. It's physically a much larger unit. It has to be to get a bigger transformer. And it's a 1-to-1 transformer. This one I think goes for about 600 bucks, and you might think that's ridiculously expensive for just it is literally a transformer inside, a 1-to-1 transformer. But try and get 1 hertz to 10 megahertz characters. I'll put up the characteristic response of this thing and try and get that performance out of a wideband injection transformer. It is ridiculously hard to get a flat bandwidth like that out of this thing. Anyway, this is used for doing voltage injection into DC to DC power supplies. Basically, you put it into the feedback path of the voltage divider, and that's how you actually get the magnitude and phase response, the characteristic response of a DC to DC converter that allows you to check, allows you to analyze the stability of the circuit with various loads, or choose the correct output capacitor, the correct ESR, all that sort of stuff designed to DC to DC converters. As I said, that is a whole couple of videos actually in its own right. But suffice it to say, this is the going price for injection transformers. You can kind of do it yourself, and you can even use like a mains transformer as a crude Clayton's injection transformer, but nothing beats this. If you have to measure a DC power supply, you're going to be forking out the $500 or $600 for a proper injection transformer. And if you think the rest of the stuff's expensive, this SMD adapter that just allows you to put your SMD part in there, and this spring, oh God, it's beautiful. And you can even adjust it like that as well. Fantastic. This thing is like $1,000 just for this contact SMD adapter. But if you're serious about, testing passive components, then it's nothing to pay something like this for a good test jig. Try and build it yourself just in time. And for those who are just pulling their hair out over my pronunciation of Bode, that's how it's commonly pronounced here in Australia. Not Bode, not Bodie, not Bode. I know that's how the guy pronounced his name, but that's not how it's commonly pronounced here in Australia. So just deal with it, all right? That's how I call it. It's the Bode 100. And of course, no expensive bit of measurement kit like this would be complete without, of course, your requisite calibration and conformance certificate. That'll keep your QA manager happy, no doubt. Hello, Marcus Mark. Marky Mark. And the Funky Bunch. Mark Wahlberg in a new life. Is he giving up the movies? Anyway, and we get one for the injection transformer as well, which is fantastic, which is what you'd expect when you pay your $500. And the test adapter as well. So, you know, it's all there. Fantastic. So this is basically one of the most professional bits of kit you can actually get for doing frequency response analysis, Vector Network Analyser stuff up to that 50 megahertz thing. So let's take a look at the software here, because that will pretty much explain everything, because I've had a quick play around with it and it looks very impressive. Of course, it's all about the software in a case like this. You know, like the hardware's like impressive in its own right, but it'd want to be for the money. But really what you're after is the software that allows you to do, really simple stuff like this. So let's have a look at the Bode Analyzer Suite 3.12. That's the one that came on the CD. I'm not sure if there's a newer one. I'll try not to chop off some of this here. But basically, looks like we've got some recent. I haven't done those. But let's have a look. We've got Vector Network Analysis, VNA, and we've got impedance analysis as well. And the good thing about this is that it shows you actually how to hook up the individual items and what they actually do. So in this case, looks like we've got 3 of them. Didn't expand them all. Should by default. Anyway, we've got transmission and reflection analysis. So yes, it can do S parameters just like the Siglent RF VNA that we looked at. It does S11 and S21, does it? Yes, S11 reflected and S21 transmitted, which is your basic 2-port Vector Network Analyzer. And you can simply just start the measurement right here. Or we can do gain phase analysis, which is your basic frequency response transfer that you get for a filter or something like that. So in this case, it's your device under test. You know, it could be a simple RC filter or anything like that, or it could be an amplifier or whatever. And this is how you hook it up. The output here, you're measuring the output directly. You're measuring the input directly on channel 1 and the output on channel 2. And we can do reflection with an external directional couplers as well. So if you're into measuring directional couplers and stuff like that, beauty. This thing will do the business. So, and in terms of impedance analyzer, look at all the different stuff it can do here. This is just ridiculous. But it's great. This is how much effort they've gone to in the software, and this is really what you're paying for, is the finesse in the software in this case. So, you know, because the hardware is not worth $5,000, right? It's, you know, and this little adapter here is not worth, you know, $1,000, right? But it's the research and the, you know, even though as great a build quality as these things are, they're not physically worth that, but you're paying for all the software and R&D and everything else. So anyway, we can do 1-port just reflection analysis. So can we do like, you know, maybe distance to fault or something like that? We should be able to see things like that. Basic impedance analysis as well. So that's what we can use this thing for, the impedance analyzer adapter, the WBIC or the WSMC adapter. So that allows us to measure our capacitors, our inductors, other surface mount components for to get a frequency and phase response over a magnitude and phase response over frequency. Shunt through, we'll probably use that for measuring. We'll just get a gain response plot of the injection transformer, shall we? Shunt through with through resistance, series through, voltage and current. So if you had a current probe, I assume they sell a current probe. I haven't looked, or you could use like a, you know, an off-the-shelf one or something like that. Assume you can calibrate the input and stuff like that, so you can use your standard voltage probe and current probe to measure that, or you can measure external bridges. So it all just installed quite nicely. There were no issues. I just plugged it in, no drivers to dick around with. It just worked. So let's go in and let's try the impedance analyzer, shall we? If we go in and start measurement, then it did, when I booted it up before, it did actually go through a calibration procedure, which took a minute or two. I'm not sure if it does that. It doesn't look like, it's not looking like it does that this time. Maybe it was only the first time it started or something. So it's probably got the hardware inside to allow automated calibration. All right, so let's go in and measure a, well, you don't know if you can see it, but a 0.1 nanofarad, I think it's a 0805 ceramic cap. So as I will link in at the end, I've done this with a crudely, very crudely, with a cobbled together a system with a VNA with a red pataya to give us the magnitude and phase response of, or was it just magnitude? I can't remember. Response of some bypass capacitors, but this is the professional way to do it. So anyway, let's have a look at the software and see what it has to offer here. Now, look at all the axes. Of course, you can do logarithmic or linear axes like that, level, constant, or variable, and you can shape the level too, which is a very interesting thing, which is really quite valuable if, depending on the frequency you're at, you may find that you get lots of noise at sort of the low end or high end or whatever, depending on the thing that you're actually trying to measure, and then you can actually shape use this tool to actually shape. How can we do it? I guess we've got to just add the points in here, reference levels, full frequency range. I haven't actually tried this, but you can actually shape this output signal level based on the frequency so that you can give you like a greater signal to noise ratio depending on the type of thing that you're actually measuring. So if you're getting lots of noise and crap on your waveform at a particular at a low end or a high end, for example, you can shape the output signal level to give you a higher level to compensate so that you get greater signal to noise level. And that is the attention to detail you get in a professional bit of software like this. They've thought of everything. That's absolutely fantastic. And we can set the receiver bandwidth. So we can set our start frequency, 40 megahertz. It does go up to 50 megahertz, this bit of kit. It's basically DC to 50 meg, which pretty much covers most stuff you would deal with in electronics, in basic electronics design. Over that, you sort of start getting into the high end side of town. You'd probably be using a $20,000-$30,000 bit of VNA kit from the likes of Keysight or something like that. Anyway, full range. That just gives us open short load calibration as well, which of course you need for a vector network analyzer. We did get some loads in I think we got the calibration kit with it. This I love, check it out. And this has, this screen will change depending on which particular mode that you're in. We're in the frequency response analysis mode at the moment, and it shows us the internals of how it works. And at the moment, we haven't got the 50 ohm turned. No, we don't. I think it's forcing us. No, I have been able to do that before. I have been able to switch the 50 ohm, internal 50 ohm load off and on. Anyway, it's not letting me, and it does let you do it at some stage. Anyway, you can see that the internal output path here can actually measure the internal reference, and the receiver too can do that. So that's how it's obviously using, there's two receivers inside, so that's how it can get the S11 reflected power coming, the reflected measurement coming back. So anyway, you can set all that stuff up. So we've got our cursors. So let's go from 100 hertz. Let's go over the full range, shall we? 50 meg. You type in meg, and we don't want to go really low frequency, otherwise it takes too long. If you set it to 1 hertz, it can take like minutes. We haven't set it up. It's not letting us do it. I'll get back to you. Aha, it's not actually going to let us do this without, this command is currently disabled, a calibration is required. So we have to go through the calibration first. I hadn't actually used this impedance response one before, so calibration it is. And of course that makes sense because we have to compensate for the jig. So it's not going to just let us run the test willy-nilly, is it? And that's why we have this screw terminal thing here, which allows us to open it. The open we're doing over the full frequency range. So it's compensating for all of our jig. Overload occurred. Whoa, I'm not sure what happened there, but I just ran it again and it was fine. Maybe there was a glitch in the matrix. I am wearing a very staticky pair of jeans on today. It's not good. I'm zapping everything. Okay, and then we take that back out and we do the short. Beautiful. And load. Well, our load resistor, in the box we did actually get 100 ohm 0.1% calibration resistors. Nice. So I'll put that in there. And it is really quite good that they force you to do this, because otherwise, if you're inexperienced, you will just, or if you're just excited to play around with it like I was, you would just run the test and you'd get something and you know, you'd think that's your response, but you're not compensating for all of the leads and everything else. And that test fixture, that's an inductor in its own right in there with the shaft and everything else. And, you know, you've got to compensate for that. Otherwise, you know, they're forcing you to do a professional measurement. So let's do our load. By default, it was 100 ohms. And, oh, short delay time so that you can manually switch it in. They've thought of everything. Little touches like that. It was like you wouldn't think of that from day one when you're writing this software. That would come about because, oh, wouldn't it be nice if, like, oh, it's frustrating and I wish it would delay by 5 seconds so I can run over and, like, press the short it out or something like that. So there's our 100 ohms. Beautiful. We're ready to go, and it's enabled our measurement now. Cool. 0.1 mic 100N cap back in there, and okay, let's run from 100 hertz to 50 meg. I'm just going to leave all the stuff default. We'll figure that out later. We don't want to run continuous. Let's just run a single sweep. That wasn't very exciting, was it? We can auto optimize. Look at that. And here's what I'm talking about in terms of that shaped variable, and we can shape the level. So we're getting all this noise down at the low frequency end of the spectrum, so our signal level is obviously too low, so we need to boost that up to compensate there. And by the way, I do like this receiver 1 and receiver 2 signal levels. Let's just run that again. Just run a single sweep. We can see receiver level 1, boom, the green bars went up. They'll turn red if they're going into overload. So you can see the signal level. Would have been nicer to have them maybe longer or something like that. I don't know why they couldn't have spread them, you know, made them double that length or triple that length or something. But it's awesome that they have that, because you don't want to be measuring down in the noise, and you don't want to be peaking as well. But it does tell you if you get an overload, by the way. So that's what we can use our variable shaping. Let me play around with it, see if I can get it. And we should get a smoother response down here. So what we can do is double click here. We're getting like 10K. I think below 10K, for example. Can we double click like that, and can we drag a second one? So there you go. That's fantastic. So at 10 kilohertz, let's just do the 10 kilohertz jump there. So, well, actually we want it above, don't we? 10 dBm higher at anything below 10 megahertz. So let's try that. But let's have a look. No, receiver 1. Oh, no, see? Got an extra wiggles down in there. Aha, so we can drag the reference level down like that. That's really groovy, isn't it? Whoa, we're getting much greater variance now. So let's go right up to 13 dBm there. Is that better? I think that's a bit better than before. I don't know. Anyway, that's what the shaping tool's for. Oh, stupid me, that was a pebcac. I was actually measuring my 1 nanofarad, not 100N. So, yeah, here's our 100N response, and that's why it was sort of like off the scale, off the 50 meg, and we didn't get any response from that. So here we go, but now we can see the magnitude and phase at, what is it? I don't know, we could use our cursor there, I'm sure. Oh, no, that's just zoom in. There you go. Can we reset zoom? There we go. So now we can actually see the red trace here, trace 1, which is the impedance, and you can get reflection and admittance, and it's absolutely fantastic. And, oh, you can set, math, which function? Oh, that's it. Plus, nope. How do I reset that? Nope. There we go. Anyway, we can see our classic response here at dipping at a particular, the resonant frequency for that particular multi-layer ceramic capacitor. And I've done a whole tutorial video on bypass capacitors, which I'll link in at the end, explaining all this. But there you go. We can actually measure that capacitor and that gives us a fantastic response. And you can see that the phase changes here drastically as well. On the blue here, it goes from minus 90 to plus 90 at that resonance point, as you'd expect. But hey, if we can do one capacitor, we can do two to try and combine the responses, which is what I tried to show in my previous video. So the 100N, so the 1N, unfortunately, the 1 nanofarad cap, it's going to be beyond the 50 megahertz range to get that resonant frequency. So let's do like a 10 microfarad or something. So let's combine a 100N and a 10 mic cap in parallel and see if we can get the double dip response in there. All right, so there's the response for a 10 microfarad 0603 cap, just some one hung low one out of the kit. So I'll try and put both in there at the same time, combine them, and we should get the dual response in there happening, one at the 1.8 meg or whatever it is, and the one at like 11 megahertz. Okay, I'll just run that again because I just got another 0603 package one. Happens to be around about the same resonant frequency there. As I said, that's going to change in the previous video analyzing bypass caps. That's going to change with the type of package that you have and all sorts of construction things to do with the multi-layer ceramic capacitor. Anyway, so I'll now combine the two of those. Let's see if I can do it without soldering. Don't want to have to dick around soldering the two. If I can get both of them, hold your tongue at the right angle, both to contact at once. Hopefully, be able to get the dual response. Yep. Oh, no, we only get the one response. Bummer. Gonna get this bastard. We got it. I've got to hold them together here. But you can see the broader response like this. In fact, let's do continuous, shall we? Watch this. Right? If I take my tweezers. Oh, there we go. There we go. We can see the much broader response there, over which the two capacitors combined is a lower resistance like that. So now let me now separate. Oh, what? Yeah, there we go. We're back to the single one. I only had to touch it slightly, and you combine the two like that. Or if you go back to just the original one, oh, well, the original one over here, there we go. So you got that sharp response combined at the like 1.5 meg or whatever it is, combined with the one at just over 10 or 11 meg, and they both together, they will give you a broader response. Cool, huh? And that's a much better response. That's a much more professional measured response than we got with our cobbled together red Patea system, that's for sure. So then, of course, we've got our cursors here, so you can set them up and you can get deltas as well for those things. So, you know, it's got all the functionality you need. So we can copy the image to the clipboard, so you can put it in your design notes and meeting notes and things like that. Impress your boss. Yeah, was your $5,000 well spent? No wuckers. You know, something like this could easily pay for itself in next to no time. It's cheap for a professional bit of measurement kit. Anyway, trace 1 and trace 2, we can actually set like Y maximum, like the 1 milli, so we can change our scale there. 10 milliohms, like that. You can change your phase response axes as well. So we can get reflection as well. There you go, for those curious. And admittance, which is basically the inverse, because that's basically the definition of it. Instead of peaking down like that, it peaks like that. And have a look at the formats we can do. Magnitude is not the only one. We can do magnitude in dB as well. We can do, well, phase, because that's what we've got down the bottom here. We can do, radians, for those radian fanboys. Got polar, real, imaginary, RS, LS, CS, quality factor as well. The quality factor of your capacitance there. Fantastic. We can do all this stuff and get all these measurements, even the tan theta as well. Terrific. We can measure the performance of our components. Of course, it'd be really nice if this went higher than 50 meg, but as I said, 50 meg is really quite capable for, you know, the majority of basic electronics applications. Certainly more than enough. There's probably several orders more than enough for your, like a DC to DC power supply analysis and stuff like that. But when you're analyzing components like this, especially the lower value ones, of course, you need the hundreds of megahertz, probably even a gig if you're into. But basically, then you're measuring RF components, and you need like an RF VNA, basically. And as you'd expect, you can actually do things like averaging and stuff like that. So we can view here, we can do average measurement. We can set 10 sweeps, that's enabled. Yeah, there we go, completed sweep. So it will, if you set it to continuous, it's not a good waveform because it's fairly clean here, but you know, we can change that. And another good thing is that you can go into view auto axis placement and you can go 1 axis per chart. So there you go. If you didn't like your split axes on the left hand side there, you can just separate them. Brilliant. So we should be able to smooth out some of that if we did some averaging, for example. So if we turn on the average and just go for our continuous, we'll have to do that over a couple of sweeps, but that's one way to reduce your a bit of your noise. But no, that's a genuine response. Look at that. But ordinarily, we would have been able to get rid of that crap. This is not the best example. And let's just use the other test jig, actually, to measure a top quality Chongx brand, one hung low brand, electrolytic. So let's whack that in. And, well, you can see it. I've already got the response of it here. We can run that again. But you can basically see that, the impedance is down. Well, what is it? Let's go down here. Here you go. You're green up there. By the way, you can just type in, like if you wanted the impedance at 100 kilohertz, for example, there you go. It immediately jumps over 82.782 milliohms. And this is why for electrolytics, for example, they measure the ESR at typically 100 kilohertz. That's what it's specified at, because it's basically resistive around that particular frequency. But as you can see, like above that, the inductance is going to dominate, and it's going to just go back up in impedance like that. So really, these are, electrolytics like these really only have a low impedance around, quite a narrow range. That's why, these aren't particularly good for like bypassing an IC, for example. And also what we've measured there is basically the ESR, the equivalent series resistance in milliohms there. 82 milliohms in this particular case at 100 kilohertz there. And so it allows you to measure all sorts of parameters of your capacitor, not just that. But, you can measure, we can go in there and measure our Q, for example, for all you Q fanboys. There you go. So that's where you want the Q, right down there. It's 0, it's pretty good over a reasonable range, but above that, it starts to go to crap. And then there's some, actually, look, it comes back down there. So there's some parasitics above, the 10 megahertz that's making it come back down. So that's interesting. So that is impressive functionality just for that one thing. How do we get home? Do we just go new? Just for the impedance analysis here. But then we can do one port reflection and stuff like that. In fact, let's just try that live. Let's just leave our coax flapping in the breeze, shall we? Do our one port, discard all our changes before. And oh yeah, and you can save to like memory and stuff like that. Where is it? Yeah, measurement to new memory and things like that. You can set up multiple memories and do all sorts of other stuff. It's really quite cool. So anyway, let's just go single. Now, sadly, I'm just using the coax like this. Sadly, the it doesn't seem to give us like a distance to fault kind of thing or anything like that. Even though in theory, it should be capable of doing that. You can make it out, but it just doesn't have that functionality built in, unfortunately. So that's just regular reflected stuff. So there's our, so if we take off our 50 ohm, we can even plug in a short, can we? There's our short. Neat. But yeah, anyway, that's just our single port reflected measurement. Okay, let's do our Y-band injection transformer. I'm very excited about this for power supply measurement, as I said, because we're working on the microcurrent and other stuff, and I'm definitely psyched to do videos on this. So let's see if we can get a performance plot of this thing. It came with the little isolated adapter, because this is, I'm not sure of the isolation voltage of this thing, but, you know, like several hundred, oh, by the way, made in Austria, thank you very much. Probably hand wound by nude Austrian virgins, the transformer in there, no doubt. So let's do a shunt through, shall we? Let's give it a whirl. Discard what we had before. Let's go. So we wanted, it's got 10 megahertz. So let's go to 20 meg, shall we? 100 hertz. And let's just leave everything default and sweep that. And there is our response. Bingo. So this is our impedance magnitude plot. And you can see at 10 meg, bingo, it's just gone to town at 10 meg. So they were right with the 10 meg bandwidth. But that's the impedance, basically the impedance of the thing. But let's go measure the amplitude response. I just wanted to show you the impedance there. So let's go back through, and we can now go gain phase. Let's give that a whirl. We will need our T-piece for that. So there we go. Channel 1 on there. And are we good to go? Discard. Okay, let's just set standard levels, and let's give it, well, we need that 20 meg, 10 hertz to 20 meg. We can go further than that. Yeah, see how it is slower at the start there? If you went to 1 hertz, it'd probably take a few minutes. So, boom, and then boom. Oh, she shot up. Oh, okay. Ah, yeah, there we go. Didn't have our 50 ohm terminator on. So let's redo our 50 ohm terminator, do that again, because our magnitude shot up there past 1 megahertz, and we should find it should now roll off. So let's do that again. But check it out. It is basically ruler flat. I'll zoom in on this. Can I zoom in while it's doing it? You bet I can. There we go. So, whoop, look at that. That is, magnitude in dB. So it's ruler flat. Look at that, ruler flat, up to pretty much up to 1 meg, and then it's going to drop off, and then at 10 meg, or no, sorry, past 10 meg, we can get our cursor there. We can actually measure that. It does, no, it doesn't really snap. Would have been nice to have like auto. I guess that's the only thing that's missing. I don't seem to have seen it, is that like auto peak detection and stuff like that. That would have been nice to have that. But yeah, at 12.6 meg there, it's rolled off. So there you go. To get a ruler flat response like that in to 10 megahertz is just insane. Let's go down to 1 hertz and we'll see. That'll actually take a while, I think. Yeah, it's not doing anything at the moment. Yep, there we go. It's just going to take a while. But to get a ruler flat performance on that sort of injection transformer over that bandwidth, wow, that is really nice. You have a hard time doing it yourself, So if you think you're $500 or $600 for an injection transformer, which is the market rate for a good injection transformer, I'm not aware of any really cheaper. I'm not sure if anyone makes any cheaper than like $500 or something like that. That's what you're paying for. You're paying for that performance. Good luck trying to get an off-the-shelf pulse transformer or widen your own. You might be able to wind your own if you know what you're doing, but a lot of experimentation. You spend more than that in hours just trying to dick around, trying to get that going. But anyway, look, down at 1 hertz there, it's bugger all. But if you need to go even lower than that for specific control loops and stuff like that, then they do sell a much physically bigger one, because it's got to have a physically bigger transformer in it that goes basically almost down to DC, which is ridiculous. I'm not sure of the exact frequency. Anyway, if you think this one's low frequency performance is good, they sell another one. which is even better. There you go. That's just fantastic response. Brilliant. And if we go in here and have a look at our transmission and reflected, our S parameter VNA stuff, let's go in here. Well, let's have a look at our hardware setup. So this is our transmission and gain. So this is S21 parameters, of course, and it shows how the internal reference has been switched. Ooh, oh look, we can live switch it. There we go. Beautiful. It's realized what we're doing and has changed it from S21 to the frequency response of the DUT. That is really nice. I like that. Brilliant. Anyway, so there's our S21 setup, and it uses receiver 1 internal. So even though I've got the coax hooked up here, it's not actually doing anything in that particular mode. And impedance and reflection, there of course we don't need anything else. So we can do our S11. So let's just run that. Now I've just still got like just the transformer hooked up. There you go. So there's our gain and our reflection as well. Now the really good thing about this is that because we've got trace 1 and trace 2, it's put them on here, but check this out, and this is what the signal analyzer didn't have. Let's say we wanted a polar plot for trace 1. Bingo, we get ourselves that polar plot there, and that's optimized, but it knows that trace 2 is a magnitude reflection magnitude measurement, so it splits the screen like that, and we can actually use our cursors like that to show the relationship between the different display systems, because that's all they are. We're measuring the same thing, whether it's a polar plot like this or a magnitude frequency response like this. It's exactly the same thing. It's just a different way to actually display it. So that's really cool. It has that capability. That's just awesome. But you know, if we wanted, we could well, then we can do the impedance there. It's just really very impressive capability to be able to split those. And if we had a larger screen, I'm sure we'd be able to display more there. There's our Nyquist. Wow, there's our imaginary. Can we zoom in on that? Optimize. The optimized zoom works really well. Just gets you straight in there. Beautiful. This works so well. I'm very, very impressed with this. It's great. And of course, you might have noticed there that our gain, because we're doing gain here, then we don't have a Smith chart response, because that is only applicable to the reflection thing. So we'll have to go down to trace. I mean, we could do it up here. Let's do it up here. Let's select reflection, okay, and then our measurement, and then our type. Bingo, we get our Smith chart and our VSWR, and so bingo, we're in like Flynn. Look at that. I'm kind of disappointed. Does that scale with the window? Yeah, it does. So if you had a bigger screen, you're going to get a bigger response on there. So that's groovy. And you can combine the two. I mean, if you wanted to have your gain polar plot down here, you could do that. Hopefully. Yay, it didn't make a fool out of me. There you go. That's fantastic. And then you can just move your cursors along on both of those, and let's scale this one, optimize that. Oh, look at that. Beautiful. It's just brilliant. Like, you know, imagine if this thing went to a gig. Like, it'd be fantastic. But that's the problem with these sort of vector network analyzers. They're basically either designed for your lower frequency end, like this one, like DC to 50 meg or DC to 100 meg or whatever it is, or they're designed for your more RF stuff. So they might start at like 10 kilohertz or something like that and go up to, you know, 5 gig, 10 gig, 50 gig if you want to spend $100,000, you know, stuff like that. So they're, you know, this is designed for the lower end sort of stuff, which if you're not into the RF side of things, this is much more useful for power supply measurements, larger component bypass component analysis, and you know, as I said, you could probably do some ground plane analysis with it, and a whole host of other stuff. So it really is incredibly useful, and it's money well spent. This is a professional tool. I haven't encountered any issues with it so far. It looks very, very polished, but that's what you expect. This is one of the best measurement solutions, one of the best measurement kits for this sort of you know, DC to 50 megahertz lower end VNA type stuff. It's just all-purpose design. That's basically, the company does some other stuff, but this is their basically their main product, their main focus. No wonder it's very polished. And once again, you can do gain calibration on here, and you can do impedance calibration. There's one thing I think is missing here, and when you actually go back out and come back into this function, it forces you to recalibrate every time. I don't see an option to actually save the calibration at all. I mean, saving is just the Bode file or whatever, so maybe that does save it. I don't know, you know. Test or whatever. Will that prevent us from doing that every time? I don't think so. I'll test that. And by the way, you can export PDF report, Excel. Fantastic. I won't try. No idea what touchstone is. I'm sure a few people are screaming at me. Yeah, I know what I use touchstone every day. Yeah, anyway, very comprehensive. So look, right, so I've saved that so we can open. Okay, so let's go back out, stick around here, start measurement, impedance analyzer, bingo. We can't, right, we're forced to redo that calibrate. Then if we go test, there we go. Oh yeah, yep, there we go, it saved it. Nice, they thought of that. Brilliant, well done. And for this adapter here, check it out, we got a very nice little short and load. You can see the on the back there, there's a short on the top, and there's the 100 ohm, required 100 ohm on the bottom, and that can just, you just pull that back, and that just goes in, does go in there like that, so you can do your open short load compensation. Beauty. Okay, so what we're going to do now is have a look at an intermediate frequency filter there, and also a crystal. I don't know what the frequency is there, I can't read it, so we're going to have a squiz at that. And let's go into our S parameters, transmission reflection measurement. Here we go, discard changes. And let's go in to 100 kilohertz to 40 megahertz. I don't think it's probably going to be like an 8 megahertz crystal or something like that. So I've got it hooked up the crystal first. Let's just use all default parameters. Oh, bingo, there we go. Looks like something's happening around about 12. Let's go to auto optimize. And let's do that again. There we go. And you'll notice that it does the dual sweep there, because it's got to change when it does the device under test, the S21. It's got to do one sweep for that, and then it does the other arrangement, which is the reflection. So it can't do those at the same time. It does those as different sweeps. So look at that. There we go. It looks like we've got our 12 megahertz. So let's go in and let's say, I don't know, 6 megahertz to give that a whirl. Oh, there we go. That's much better. We didn't see it before. We didn't capture the reflection on there because we weren't in enough. If we actually get some more points on that, we'll get higher resolution on that. Whoa, look at that. That's serious business. There you go. Got some artifacts there that we didn't see before. So let's actually, let's go 10 meg to 14 meg, shall we? Wow, look at that. You can really see. We can actually zoom in on that if we really wanted to. There we go. Look at that. But that is our resonant frequency of our crystal. Just a smidge under 12 megahertz there. It's not quite bang on, is it? So, by the way, this I believe does have like a 2 ppm crystal reference in it. It's pretty good. 11.5 meg, 12.5 meg. There we go. Let's give that a whirl. Bingo. Wham! Look at that. Boom. And there's the reflection characteristics. There you go. By the way, we can add quotes as well. So that's handy, just when you do your screenshots and stuff like that, describing your test setup and things like that. That's neat. Someone was thinking. So this is actually really cool, because what it shows us is the multiple resonant points of this crystal. These are the two primary ones. I mean, we can reset the zoom there. Like, we've got other ones here, but they're lower amplitude. What we're interested here is these 2 points here. Now, one of those is going to be the series resonant frequency, and the other one's going to be the parallel resonant frequency, depending on how you load the crystal and actually resonate. It's going to have slightly different. So if we actually go in there, and for the reflection, if we get the Q, here it is. Let's have a look at that. Oh, we're off scale. Let's auto-optimize there. Look at that. There's our parallel resonant frequencies, and that one is close to, pretty close to 12 there. We would have to, you know, go finer and get like an 11.9, 12.1 or something like that, or simply just get more points. There we go. Whoop. Whoopity-doo-dah. Beautiful. Fantastic. So that's a smidge under 12. There you go. 11.997. There you go. You can calculate the error there, whether or not that's error in this crystal, which probably isn't as good as the one inside the Bode 100, because I believe it's a 2 ppm class job. But isn't that neat? There you go. Oh, and we've got a memory display on there, so we can actually, that's the good thing about the memory display, you can actually overlay previous results and stuff like that. Fantastic. So you don't have to like post-process any of this stuff. You don't have to export it, and you can, you know, do it inside the program and then do that one nice PDF report or screenshot. Beauty. And you can see the ridiculous value of Q there for the for the crystal. Look at that, 21,000, 22,000, something like that, and 0 down here just at either side. That's how selective quartz crystals are, because they resonate at that one frequency and that's it. That's what makes them brilliant. So hopefully you can see by this that this is a brilliant tool for analyzing like just components, crystals, resonators, filters, piezo ceramic transducers and stuff like that. Would have loved to have had this when I was working on underwater hydrophones and stuff like that to characterize them. You know, we used you know, not as modern instruments as this to do that back in the day, and this is just fantastic. We can go to town with all the different measurement options and stuff like that. It's brilliant. This is just something you can't do. Like, you can kind of like cobble this together with other tools, but like, no, you get this and you do the job properly. And we should be able to do some more analysis through some sort of through, where's the through one? If they, yeah, series through they call it. There it is. So let's do that. Discard changes. So we're not doing our VNA, so we're not going to get any reflection type stuff from this. But we can run our 10 meg to 14 meg there. Zippity-doo-dah, zippity-day. So we'll just zoom into that. But we'd better actually perform a through calibration on this thing. So let's try that, shall we? So impedance calibration, full range. Let's just do the full range. Through calibration, start. So we're taking out the cables. We're compensating for that. Beautiful. Done. Advanced settings. We don't want any of that. Open short load. Nah, not worried about that. So we're good to go. So let's actually widen that from 10 to 14 megahertz and do a sweep on that. There we go. Now we should be able to actually work out the parallel capacitance of this particular crystal. Okay, so to get our parallel capacitance, let's turn off trace 2 here, because that's annoying. Instead of impedance, let's go to admittance. Ah, do we have to redo it? No. Auto optimize. There we go. So what we want to do is go away from the resonant point, and we should be able to change the units or the format. Yep, there we go. There's the parallel capacitance, CP. Beautiful. And that should give us... Oh, sorry. Wrong one. Let's go up here. Admittance. There we go. Parallel capacitance. Ta-da! And bingo, that gives us the result up there. There we go. So we want to go away from the resonant. Optimize. There we go. Want to go away from the resonant point, and you'll find that the trace capacitance, there it is. Just over, smidgen over, half a bee's dick over, 3 picofarads. Fantastic. Because the crystal, of course, the reason that we're able to characterize this crystal is because it's not just a capacitor. It's not just the 2 plates with the quartz. It has parasitic components just like any capacitor does. There's a series resistor, series inductor, and another series cap in there, basically in parallel with that. But there you go. We can measure directly with this thing the parallel capacitance. Brilliant. So from those resonant frequencies there and these measurements, we can calculate things like the series inductance, you can calculate the quality factor, and all sorts of stuff to do all the parameters of your actual crystal under test. Fantastic. It's just using your basic formulas for your equivalent series of your crystal. And I just switched over to our IF filter there, which should be a standard 10.7 meg. And sure enough, I'm still on the admittance and parallel capacitance range here. And sure enough, you can see the peak there at your, well, basically, yep, at 10.7 meg. Beauty. But of course, you don't have to do the admittance. You can go back and do all your other stuff. And single, auto optimize. There we go. Woo! Really see that impedance go right down to buggery. Well, not buggery, but it goes right down there at that resonant point. And once again, we're getting this noise and crap in here because they're like, it's right down. Now we can, because it's right down in signal level, so we can fix that up by either changing our magnitude, or we might be able to change our receiver bandwidth. Let's go down, let's drop that by an order of magnitude down to 30 Hertz, and let's sweep that again. And yep, we're getting an improvement. It's going to be slower, of course, with the lower receiver bandwidth, but we should see this clean up a tad. Bit more accurate. Yep. Go back to 300. Drop that down to 10 dB. Run it again. Yeah, it's a bit better. There you go. And well, what was that? Can we go to 0? Not going to overflow, are we? Look at our receiver signal level down there. Nah, it's hunky-dory. There you go. So we were right down in the noise there pretty much. So I think we'll leave it there. There is a ton more stuff I can do with this thing, which I will save for other videos, because I don't want to spoil it. Things like I would definitely going to do a separate video on the wideband injection transformer, and using that to do voltage injection, which is one of the techniques to do power supply regulation stability testing and stuff like that. So we can, it's a whole bunch of videos. If you want to see me do, if you've got a suggestion for me to do a video on something, now I've got this bit of kit here in the lab, there's just no shortage of stuff I can do videos on. It's absolutely fantastic. So thank you very much, Omicron Lab. Obviously, that gets a massive thumbs up. It's just, you could argue, yeah, it's a lot of money to pay, but the software looks very professional, very comprehensive. Haven't found any issues. And I haven't done a teardown yet. I'm going to have to do a separate teardown, but I'm sure the hardware's really nice inside. Anyway, and I want to see, hopefully, we can see inside this wideband injection transformer if they haven't potted it. I don't know, feels a bit hefty, but yeah, this is a brilliant bit of kit. And if if you've got a lab budget or something like that and you're wondering what else to buy, and like $5,000 is suitable, get something like this. There's just so much stuff you can do with this, especially like if you're into power supply design and stuff like that. Something like this is an absolute no-brainer. Maybe muck around with PCB, bypassing and stuff like that. Let me know in the comments what type of video you'd like to see with a bit of kit like this. It's just absolutely incredible. So yeah, I think it's worth every cent. So yeah, it's not for every lab, and yes, it is pricey, but I'm not really aware of as comprehensive a solution as this for anything less cost. If there is, let me know and I'll check it out. But yeah, this is just absolutely fantastic. I love it. Works brilliantly. Oh, I'm just picturing all the videos I can do with this. It's fantastic. Anyway, hope you liked the video. If you did, please give it a big thumbs up, and there should be videos at the end here. Hopefully a teardown, maybe, if I get that done and uploaded I might release them at the same time. I don't know. Anyway, hope you liked it. as always, discuss on the EEVBlog forum down below. Catch you next time.